In 1940, the Tacoma Narrows Bridge tore itself apart in a 64 km per hour wind. Engineers had done the structural calculations. What they hadn't predicted was how air itself would behave around the deck. Today, a single CFD simulation would catch that failure before the first bolt was tightened. In the next 9 minutes, you'll understand what computational fluid dynamics is, how it works, and why it's one of the most powerful tools in modern engineering. Later, I'll show you the one mistake that makes half of all CFD results meaningless. At its simplest, CFD is the science of using computers to predict how fluids behave. The physics governing flow has been understood for nearly 2 centuries through the Navier-Stokes equations. The problem? For anything beyond trivially simple geometries, these partial differential equations have no analytical solution. So CFD takes a different approach. Instead of solving the equations exactly across a continuous domain, it breaks the domain into thousands or millions of small discrete cells. At each cell, the equations become algebraic systems a computer can solve. The finer the mesh, the closer the approximation gets to reality. That trade off between resolution and computational cost is the fundamental tension in every CFD simulation. Every CFD simulation is built on three conservation laws: conservation of mass, described by the continuity equation; conservation of momentum, Newton's second law for fluids; and conservation of energy, the first law of thermodynamics. Together, these form the Navier-Stokes system. The momentum equation is where the real complexity lives. The transient term tracks how velocity changes over time. The convection term captures momentum carried by the flow itself. And this is the nonlinear term that makes the whole system so difficult. The pressure gradient drives flow from high to low pressure. The viscous term represents internal friction, and body forces account for gravity. That convection term is what makes turbulence chaotic and impossible to solve analytically for real engineering problems. Before you solve anything, you need a mesh. Divide the fluid domain into cells, each storing velocity, pressure, and temperature values. Structured meshes use regular hexahedral cells, efficient and accurate, but hard to fit around complex shapes. Unstructured meshes use tetrahedral cells that conform to complicated geometries, but need more cells. Most real simulations use hybrid approaches. Regardless of type, mesh quality is critical. Poor aspect ratios, high skewness, or low orthogonality introduce numerical errors no solver setting can fix. In a moment, we'll see how the best physics setup fails if the mesh isn't right. Every CFD simulation follows three stages: pre-processing, solving, and post-processing. Pre-processing is where most of your time goes and where most mistakes happen. Start with geometry. Import a CAD model, extract the fluid domain, then clean it up, removing gaps, overlaps, and tiny features that add unnecessary cells. Then mesh the domain, refining in critical regions like boundary layers and wakes. Finally, set boundary conditions. Inlets define what enters. Outlets define where flow exits. Walls enforce no slip. Symmetry planes have your computational cost. Get any of these wrong, and it doesn't matter how good your solver is. Garbage in, garbage out. With pre-processing complete, the solver visits each cell, assembles algebraic equations from the discretized Navier-Stokes system, and solves them iteratively. It makes an initial guess, computes the residual error, then updates the solution. Iteration after iteration, residuals drop. When they reach a target threshold, typically 10 to the minus 4, we call the solution converged. But here's the critical insight beginners miss: low residuals alone do not guarantee a correct solution. You need to monitor the quantities you care about: lift, drag, pressure drop. A residual can flatten at 10 to the minus 3 while your drag coefficient oscillates wildly. That's not convergence. That's a solver that's stuck. Post processing is where your simulation becomes useful or where you fool yourself. Contour plots map velocity, pressure, or temperature onto color. Streamlines trace particle paths. Vector plots show direction and magnitude. These tools are powerful but dangerous. A contour plot will look beautiful even if your mesh is too coarse and your boundary conditions are wrong. The colors don't care. This is why validation is non negotiable. Compare results against experimental data or benchmarks. Perform a mesh independent study. Run three progressively finer meshes and demonstrate your results converge. If they don't, your answer depends on your mesh, not on the physics. CFD saves money, time, and sometimes lives. A wind tunnel test costs tens of thousands of dollars. A CFD simulation runs on a workstation overnight. CFD also lets you explore conditions impossible to test physically: hypersonic reentry, internal combustion, blood flow through a diseased artery, and it gives you the full picture. A wind tunnel measures forces and surface pressures. CFD provides the complete velocity, pressure, and temperature field at every point in the domain. GPU acceleration is cutting simulation times from hours to minutes. Cloud platforms are eliminating the need for in house clusters. The global CFD market is approaching $10 billion because the return on investment is undeniable. Most engineering flows are turbulent, chaotic, multi scale, and fundamentally unpredictable at the smallest scales. Solving the full equations at every scale is direct numerical simulation, and the cost scales with Reynolds number cubed. For an aircraft wing at cruise, you'd need more computing power than exists. So we model. The industry workhorse is RANS, Reynolds average Navier-Stokes, which time averages the equations and models turbulence with additional transport equations. Common models include K epsilon and K omega SST. Large eddy simulation resolves large eddies and models small ones. It's more accurate but 10 to 100 times more expensive. Choosing between DNS, LESS, and RANS depends on accuracy requirements, computational budget, and what you're predicting. Pitfall 1: Trusting the contour plot. A beautiful velocity field doesn't mean a correct one. Always validate against experiments. Pitfall 2: Skipping mesh independence. If your answer changes when you refine the mesh, it depends on your mesh, not the physics. Run at least 3 levels. Pitfall 3: Wrong boundary conditions. Outlet too close, incorrect inlet turbulence intensity, symmetry where the flow isn't symmetric. The solver converges happily to the wrong answer. Pitfall 4: Ignoring Y plus requirements. Your turbulence model needs a specific near wall mesh resolution. Violate it, and wall shear stress, heat transfer, and separation predictions are unreliable. The pattern is simple. CFD always gives you an answer. Your job is knowing whether it means anything. CFD has come a long way from 1960s aerospace research. The software ecosystem spans commercial solvers like ANSYS Fluent and Star CCM Plus, alongside open source tools like OpenFOAM and SU2. But the real transformation is computational. GPU acceleration delivers 10 to 30 times the speedups. Cloud platforms make high performance computing accessible to small teams. Machine learning is augmenting traditional CFD with physics informed neural networks and surrogate models enabling real time design exploration. Digital twins connect live sensor data with CFD models. The tools keep improving, but the fundamentals: Navier-Stokes, meshing, validation, physical intuition, those never change. CFD converts continuous Navier-Stokes equations into discrete algebraic systems computers can solve. The workflow is pre-processing, solving, and post-processing, and result quality is determined by your setup, not your solver. Turbulence modeling is the biggest approximation. Validation isn't optional. Whether you're simulating airflow over a wing, coolant through a battery pack, or blood through an artery, the fundamentals are the same. Master them, and you can run CFD in any software, on any problem. Subscribe for weekly CFD fundamentals. Next week, we're diving into meshing, the one step that makes or breaks every simulation.